Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert de Nameland, who has been the greatest living philosopher before me. So, in this video I want to talk about this paper that has just appeared. I'll give all the links in the description, obviously, so you can download it right now, you can share it right now, you can also share this video as a means of sharing the paper itself. All of that would be welcome. So, what's it about? Well, the authors are Jacob Gable and myself, and it talks about crater formation under extreme space weather conditions, which sounds pretty interesting, doesn't it? Well, let's look at some details. So, craters might be produced by electric currents, both in laboratory conditions and on celestial bodies. An extremely large solar outburst or a nearby supernova may cause cratering of solar system bodies. Then laboratory electric discharge machining is a useful tool for studying large-scale craters. Piezoelectricity may play a major role even in impact cratering. And finally, electrically induced cratering may solve some problems of impact crater hypothesis. I won't be reading the abstract, but it's fairly condensed, fairly focused. So you can do that on your own, and it contains most of the ideas given in the paper, though I would still recommend you reading the paper itself. All right, so we shall talk about like the theory and some of other details a little bit later in this video. Let's look at the conclusions. So what do we conclude? So we develop a theory, again, we'll look at it a bit later, of electric discharge machining of planetary surfaces as a viable alternative to impact crater formation. We conduct experiments. It was Jacob conducting the experiments. So they are actually very simple. So you can potentially just do experiments of your own of the same sort. And they are very low cost, but they do acquire some interesting results. However, in terms of like scaled up situation where we're talking about like actual celestial bodies and actual large craters, up to maybe 1,000 kilometers large, actually, we show that a CME that would be like 1,000,000 to 1,000,000,000 perhaps, or 10 billion times larger in terms of the mass. There's an Easter egg, by the way. You can read it if you wish. So, such a large CME is enough in terms of energy to produce the largest craters in the solar system, like 1,000 kilometers large again. And all the like smaller craters can be produced even by smaller CMEs, all right? So we even propose to like look at the more recent craters and see if they can be associated with some recent CMEs. I mean, like there's like a case study with this crater on March that appeared on March 15th, 2013. Okay, what else do we say? Well, that previous like estimates of cratering of the moon have been kind of lower than what is actually observed. So this could be potentially attributed to ongoing EDM cratering even right now with like modern levels of solar activity. We embrace the possibilities of plasma scaling. Again, we conduct a small scale experiment, which actually, like the energies required, can be calculated like this. Here D is the diameter of the crater, T is the energy that you have. So in our case, we've had something like 45 kilojoules, and according to this formula, this corresponds to a crater of diameter of 8 centimeters, which is a very good fit to what we actually got. Like here are some pictures made by Jacob from his experiments. You can, of course, look at them. There's also a couple of videos, by the way, and there's a link at the very end of the paper to like a Google repository where you can, Google Drive, where you can actually look at the pictures themselves and the videos as well. There's 2 videos. Okay, yeah. This could maybe also be an explanation for the so-called late heavy bombardment, which is a hypothetical occurrence in the history of early solar system where suddenly, like, all the bodies in the system became like blasted by something, like the cratering rates just skyrocketed for no apparent reason. And maybe if that was a period of like enhanced solar activity, that would explain that, because like think about a big CME, like it covers most of the system, right? So it can cause basically simultaneous cratering on every planet, right? So that would make sense. Uh, yeah, we also use this paper by Satterfield. Well, it's not like a paper, it's like a website he has where he summarizes like the differences and similarities between electric discharge craters and impact craters. We have a little bit of a debate with him. I mean, not a, like actual debate, but you know, like secondary, you might say. Okay, so what about the model? Like, how can currents appear from, for example, this cloud of plasma? It was actually pretty simple. So this paper is probably the only paper that actually tries to derive a mechanism, like an actual physical mechanism of cratering through EDM of celestial bodies. And so this is my model that I have proposed. Actually, like I took most of it from Alfvén. I should correct this. I need a longer dash. So anyway, what happens is if we have like this cloud of infalling magnetized plasma, falling onto some surface. Let's say this is a planetary surface. So this plasma drifts along the equipotential surfaces, right? And it wants to go away, you know. It wants to deviate because like it can't pass through the surface, right? So it has to go someplace else, and it does. And in order to do so, an electric current should appear. This one, the darker blue one. So this current is the so-called inertia current, and it does exactly that. Like it serves the purpose of deviating of plasma, all right, through the Lorentz forces. Basically, it's like a coil, right? A magnetic coil, which again, deviates the plasma through magnetic fields, right? And it is this current which I assume could cause cratering, because look at here, in these places where it actually connects to the surface, it should be closed by the way, but in these places where it connects to the surface we can have cratering and potentially some other effects like that. So this is the basic, like the most simple idea imaginable, right? So I actually give a comment there, like in the end, near the end of this section, where I talk about how, well, this is obviously like zeroth approximation, you know, like potentially some higher order effects, some more complex plasma dynamics may happen, but this is like the simplest of the simplest that we could have come up with. Okay, so I make some calculations. I say that basically the energy available to this current would be determined by, strictly speaking, the sum of kinetic energy of plasma, its magnetic energy, and its electric energy. But here I only take the kinetic part. Where is it? It actually disappeared for some reason. Like there should be another equation over here. So later on, I actually do a full evaluation like this. So here we have the kinetic energy of plasma. This is the electric field energy. This is the magnetic field. And actually, like the electric field is really, really weak compared to the magnetic energy. So we can just neglect it right away. But you can see from this expression that usually the magnetic energy is also pretty low compared to the kinetic energy, at least for like the calm solar wind. And maybe it's not the case in case of these like hypothetical stronger solar outbursts. I don't know. This may be a possibility. Like for Carrington event, it's actually like the magnetic part is assumed to be relatively similar in terms of orders of magnitude to the kinetic part, but it could be either way. Anyway, so yeah, this is how we estimate the energy that we need for our plasma cloud. Then I actually calculate. This is the heat that would be generated by this current, and it is this heat that essentially produces the crater, because electric discharge machining is essentially a thermal process, right? It's the craters are produced by heat. And this is exactly what we assume here. And where's my calculation? There it is. So here I make an estimate of the needed fraction of the mass of the sun, for example, which would be contained in this CME. And it should be something like 10 to the minus 10th to 10 to the minus 6th. That depends on the velocity of plasma. So 10 to the minus 6, so 1/1,000,000th of the solar mass must be ejected. And I repeat, that's to produce the largest craters in the solar system, right? There's only a handful of these, like literally 3 or 4 or something like that. And these are like basins on the Moon and Mars. And for smaller craters, you don't need that much energy. Okay, so what else is there? What else is interesting? The piezoelectricity is actually surprisingly overlooked in pretty much all of the impact studies, as well as many, electrically related studies, if any. So here I, for example, calculate that even for the impact crater formation, assuming the pressures that are again assumed to exist there under the impact, under the influence of an actual impact, there should be an electrical breakdown of the surface. For example, if it's made of quartz, like I make the explicit calculation here for quartz. So yeah, interesting stuff. What else is there? That's probably all, actually. That's probably all. You can read the paper. There's a lot of like various ideas spread here and there. So maybe you'll notice something that I have overlooked right now. Yeah, so where does this paper come from? Well, I'm glad you asked. It's from here. So I propose to any one of you who wants to work on developing their own theory, like we can collaborate, and something like this may come as a result, because this is exactly what happened to Jacob. Like, he subscribed to my coaching, he went to my Patreon, he took this one, read the description please, and this paper is exactly the result of this process. So if you wish to participate, if you have your own theory that you want to work on, then go to my Patreon, subscribe here, just again read all the disclaimers over here, and we'll work on your theory and produce a paper like this one, for example. Alright, again, share it with anyone potentially interested, or even not. And yeah, thank you for watching. The eons are closing.